Parnell from the University of St Andrews, and we make the transition to magnetic fields in astrophysics, and here in the sun and the magnetosphere. You can see from this slide that Clare has been working on this for nearly 600 years, coming up to the 600th anniversary of the University of St Andrews in 1 year's time. So congratulations on that. Clare, over to you.
It certainly feels like I've been working on this for 600 years. So I was actually going to say something about the 600th anniversary of the University of St Andrews. It's obviously not as old as Cambridge. It's the third oldest university in the UK. And although it says on this slide from 1413 to 2013, it was actually in about 1410 that they started teaching. But in those days, and especially in St Andrews with its cathedral and its Catholic connections, they had to get the whole venture ratified by the Pope. So somebody set off to go and visit the Pope, and it took him quite a long time to get there, get everything signed and brought back. So by the time he returned, it was 1413, which is why we've been celebrating actually the 600th year for the last couple of years, because when did it really start? So I thought I'd better start off with a little bit of an introduction to the sun. Apologies to Nigel that I'm going to start in the solar atmosphere, not where the magnetic field is generated inside the solar interior. But obviously understanding that is very important, and Cambridge has been a world leader in understanding that. So the surface of the sun, photosphere, this is sort of an image of the sun you might sort of recognise. It's in white light, and we have a sunspot here, and this is shown in quite a lot of detail. So we have very high resolution images. But if we look here, this is a picture of the magnetogram, and then if we fade in, we go through the chromosphere, which interestingly is slightly warmer than the surface of the sun, and it can be observed in many different wavelengths. As you can see, there are features that are all corresponding with these sunspots we have. Then we move higher up into the outer atmosphere of the sun, and this is even hotter still, at 1,000,000 degrees, some about 200 times, 250 times hotter than the surface. And here you're beginning to see the sort of magnetic field structures. I'll play this again. Hopefully this will work. Does that sun change shape, or it's just me? It's just me from the angle I'm looking at. Right. So here you can see the magnetic field structures, the strong sunspots, which are down here, are associated with the bright regions on the sun. And so much. What is the significance of changing colour? You're moving out? Basically moving out through the atmosphere. It's observing the sun in different wavelengths, and the different wavelengths will identify different temperature of plasma. Okay, so plasma is at different temperature, and as you can see here, different regions are brightening. So when you look at these images on the sun, I'll go to the next thing here. This is going to be a movie of the solar corona, and you'll notice in this, as it's playing, oh no, let me go back, I need to click on this, that here the whole of the atmosphere isn't all filled in one colour. This will play. It will. It was all playing beautifully. There it goes, yes. Right. So you can see these loop structures around here and around here. Now, why are we identifying loop structures? Why is the whole thing not just hot? Well, the reason is because thermal conduction along field lines is 13 orders of magnitude greater than thermal conduction across field lines. So if you inject energy in one particular location, it'll spread along the magnetic field there, but it won't spread everywhere. And so as you can see on this, just huge things happening all the time, especially in these bands around here, known as active region bands, where the main sunspots are. But there are lots of other little bright points as well.
It's the corona.
Yes?
But the circle that we see is the photosphere, is it?
Well, the what you're observing here is plasma that's emitting at about 1 million degrees Kelvin. So it's stuff as low down as this is emitting at 1 million. It doesn't all emit, though, at the same height. So basically from the surface all the way upwards, well, not quite at the surface, but just above the surface all the way upwards, you can have plasma that it's about 1 million degrees. And you can have stuff that extends quite far out, or some that's quite sort of low down, depending on the magnetic field structures on which this plasma is tied. I'll just play this again, because I'd like to identify a particular region which is going to emerge around here quite soon. Here, it's going to appear around here now. And as you can see, it's emerging. There's obviously a lot of change in topology, in particular around here. There are field lines that are now connecting over here, which clearly couldn't have existed before. This has occurred through changes in the topology, in reconnection occurring of these field lines. So what I'm interested in is understanding how this reconnection occurs, and in particular that involves understanding about the topology of these fields. So, because these movies are so nice, I shall show you some more. This is a coronal mass ejection. Look at the incredible sort of twisted structure that you're getting. Now this plasma looks as if it should be free falling, but it can't. It must be tied to the field lines. And you can see that again through the way it falls down and then kind of moves along a bit and then goes down. It's much shorter. Play that again. So in particular, if you look down here, some of this plasma will sort of fall and then move along. In particular, that stuff there. And here, a lot of this stuff is kind of falling back. Understanding how all this works, how the process is sort of key things that are required on the sun. And again, here, this plasma is all tied to the field. You can see sort of a twisted structure as this plasma lifts off. These are the coronal mass ejections. They're the ones that, if they're directed towards the Earth, this one is not directed towards the Earth, but these can have significant effect on our satellites, telecommunication, or military, well, any form of satellite, and can give us the aurora and things. So this is a still image, but showing the incredible twisted structures that you get in this field. These magnetic fields are quite complex in their structures. They're not simple at all. And this is a flare. Just going along, there's some plasma downflowing, some possibly cooler or hotter plasma downfalls, and then these beautiful loop structures that are created. And obviously understanding this is sort of a key question of understanding how the magnetic field can evolve to give you structures like this. Now, because we can see global restructuring in the magnetic field, we believe that magnetic reconnection must be important for this. So, before I move on and say anything about magnetic reconnection, just to mention, unfortunately we don't have lovely global kind of movies like that of the Earth's magnetosphere, because we only have in situ instruments that will measure particular plasma parameters at particular points in the magnetosphere. But the reconnection give rise to aurora, which are associated with magnetic field structures. Here, this is on Jupiter, and this is, well, the space shuttle looking at the Earth's aurora around here. And these are normally set off by events such as solar flares or coronal mass ejections, blasting stuff out from the sun and disrupting the Earth's magnetic field.
Now, because it would be hard to describe the previous image when you showed the loop structures.
Was most of the mass in the surface of that structure that we could see, or is there a way to image below that surface? I'm just wondering what's expected. Is it
okay, so
region, or is it just the surface?
what you're looking at here,
It was really the previous one, but I realized you're going to show so many images.
yeah, so if we look at this one here, this is kind of sort of a loop structure as well. This is just highlighting the plasma at that particular temperature of the particular wavelength.
I see.
So what is the rest of the plasma like? It's a good question. You can get some evidence of that by looking at different wavelengths and therefore different temperatures. But it's difficult to say exactly what everything is because you can't see everything all at the same time. But certainly, this is basically where most of the heating is occurring, although there may be quite a lot of, in fact, there will be a lot of plasma lower down, which is cooler. So as I've alluded in looking at those movies, magnetic reconnection, well, it's a fundamental plasma physics process, applications well throughout astrophysics. And what does it do? Well, it permits a global restructuring of the magnetic field, which is very important for coronal mass ejections, for flares, and for general just heating on the sun. It produces a rapid conversion of magnetic energy into, well, three types of energy: thermal energy, bulk plasma motions, and particle acceleration. Now, reconnection operates on a wide range of scales, on the microscopic to the macroscopic. And on the sun, that means for the microscopic, we're looking at kind of iron gyro radius type length scales, so maybe 100 meters, maybe a kilometer, tens of kilometers if we're lucky, up to the macroscopic scale, which is about 1,000 kilometers or 10,000 kilometers. So there are many scale orders between all of these, and unfortunately we can't model them all in one go. So I shall be focusing on MHD models, which is looking at the sort of macroscopic evolution. Very quickly, in 2 dimensions, how does magnetic reconnection occur? Well, it must occur at X-type null points to get reconnection as opposed to annihilation. It occurs at a single point, this point in here. The field line mapping is discontinuous. If you follow this red field line, it's anchored here to begin with, and then it flips over and it's anchored on this side. The pairs of field lines break and recombine into 2 new pairs, as this little kind of animation is showing you. And you need a stagnation type flow, bringing the magnetic field in towards the little diffusion region and then outwards, taking newly reconnected field lines away. What about in 3 dimensions? Well, it doesn't have to occur at null points. It can occur in the absence of nulls. The reconnection occurs not just at a single point, but throughout a diffusion region volume. In fact, continually and continuously throughout a diffusion region volume, which means that the field line mapping is not discontinuous, but can be continuous. And the pairs of field lines, now that they'll break, but they won't recombine into 2 new pairs of field lines. What you'll find is that you need to look at surfaces or volumes of flux, and they then can recombine. And this is done through a kind of counter rotation. Now let me show you a little movie.
Can I ask an elementary question? What's the definition of reconnection?
That's a question that people have been asking over, well, about the last at least 20 years. And basically, it can be said to be associated with a region of non-idealness or diffusion region where you have the integral of E parallel is non-zero. But that doesn't actually mean that you get a global restructuring in a magnetic field. It can just mean that you get a slippage, and so so some twisted flux tube can then end up being a straight flux tube as you get your counter rotation. Things go around. So, but people argue between diffusion and true reconnection. Basically what's happening is your field lines, they go in, they'll enter a region of this non-idealness, and the plasma elements that are tied to the magnetic field, because everywhere else, wherever the magnetic field line goes, the plasma elements must travel along with that field. But when they're in the region of non-idealness, the plasma elements can basically disconnect from these field lines. So the magnetic field can slip through the plasma. And that means you can get this sort of relabeling of field lines. Because obviously field lines are not real, they're just lines of force. But they're very useful, as are streamlines. So if I show in 3 dimensions here, this is showing you there's no null point here. We've just got two flux tubes, and as they move in, they reconnect, and they can see a sort of counter-rotation in the flows. And here, I don't know if you can see it properly, but the two surfaces are linking like this. Okay, in the end, they've not mapped on one-to-one, they're linking like this. So you can find surfaces that map together, but you've got to be very clever about it to get them. Okay. So, the basic topological structures of a magnetic field. Well, there are null points, points where all three components of the magnetic field are equal to 0. And in 3 dimensions, what do they look like? Well, I've drawn the local magnetic field around one here. Here we have a separatric surface, this kind of blue plane with field lines in, and then this sort of line down here, it's the spine line. So this might be more familiar to you in that just the field is coming down and then sort of spreads out in a plane. 5 degrees. So this is supposed to be a situation where you'll get very little reconnection. It's not supposed to be a particularly exciting one. And this interplanetary magnetic field is basically being driven towards the Earth at about 400 kilometers per second. So what do we find? Well, in terms of the null clusters, we get 4 persistent null clusters. Most people would imagine you just have 2 associated with, well, group A down here, which has a topological degree of 1, which means it has a negative null point at the bottom here, and D has a topological degree of -1, which means it has a positive null point. Now, the null clusters A and D don't just have single null points, but they have different numbers of nulls. This is time against the number of nulls. And as you can see, for these A and D, you always have an odd number of nulls. And for groups B and C, you always have an even number of nulls. The groups B and C have topological degree of 0. They have even numbers of positive and negative nulls. So overall, the topological degree of any individual cluster must be, it can be positive, 0, or negative. The overall topological degree of any individual cluster must be preserved, and it obviously must be preserved in the whole domain, unless you manage to sort of move one of these null clusters out through your domain boundary. Now, a null cluster with a topological degree of 0 may actually appear from a distance as if it's one with a topological degree of which is non-zero, i.e. it may have one dominant null of some particular polarity, which is what happens in group B here. It actually looks like it has the same topological degree as group A, and it behaves as if it's got a positive null point. Negative. Now, what I'm going to do here is I'm going to move this plane back, and we're going to kind of slide it back, and we're going to look at cuts through the separatric surfaces. So these are the null points which are creating separatric surfaces. The yellow lines are the separators, and green are just a few random field lines. And what you'll see in the plane, which I don't think I can play on here. So if I stop it here, these lines here, which are black in this thing, they're the separators. On the day side, the Earth is behind. This outer circle, we're plotting an isosurface of current here, or contours of current. This is actually the bow shock. So this strong current is associated with the bow shock. It's not associated with something particular in the magnetic field in terms of kind of a magnetic field effect. It's more of a kind of a plasma effect from the bow shock, from the deceleration of the very fast solar wind. And inside here you can see an inner circle of high current, and overplotted on that are the separatric surfaces. So there's current basically around the edges of the separatric surface. And as we move behind the Earth, again, you've got this, well, this is the bow shock. It's increased, and it's about to move out of the domain. This inner circle here, again, associated with this blue separatric surface, which is going around here, which is a bit wiggly around in that region. And then you've got the positive separated surface around here, and again, it's a bit wiggly inside in there. And you've got separators, which are here, where these blue and the red lines cross, and again, separators up here where the blue and the red line cross. Then they cross in kind of multiple locations. If we continue flying through, you can see that the separatoric surfaces here have moved towards one another. And they're about to actually start overlapping to give us this big mess of separators all at the back here. So as we fly through, you've got this sort of plane here where the separatoric surfaces are crossing and intersecting, and that's where your separators are, and this is where lots of reconnection is occurring. So if I play that again. Because there's so much drawn here, you can't quite see, but this is basically the main plane where the current is. There's current around here, and there isn't really current elsewhere. So this is basically what the Earth's here. You can just about see it back. You've got some residual current from where these separated surfaces, they're no longer overlapping here. You just have them kind of snaking around. This red one snakes around, curving around like that. This one curves around like this. So they've managed to sort of detangle themselves at that stage. This is just the stills of the what I showed you before, and these are cuts in a plane, so you have nice circles on the day side, on the night side. You've still got the evidence of these circles, but inside you've got this big mess, which when it interacts and overlaps, that's where you get the separators. Now note there's a particular angle to this here. It's all lying at about 45 degrees, which happens to be the angle of the IMF, the overlying, or the interplanetary magnetic field. So what we find is, this is the Earth's magnetic axis, this is the IMF, and the night side separators, which are behind this mess here, are angled basically with the IMF, and the day side are angled halfway in between the Earth's magnetic axis and the interplanetary magnetic field, which when you think about it is quite natural, but people never really thought about it like that before. So this is basically where the separator is occurring, color-coded again with, according to parallel, so this is the main region of reconnection where basically the IMF is being forced up against the magnetic field on the Sun, on the Earth. So very quickly, if you look at cuts of basically the topology, we've taken the 45-degree angle, so this is the plane, same angle as the interplanetary magnetic field, and this is density, so this is the bow shock here. We get an increase in density, but as you can see inside, the red cuts through the separatoric surface, blue cuts through the separatoric surface. Inside, where the enclosed in these regions where you just get the Earth's magnetic field, or magnetic field connected directly to the Earth or to the Earth and the IMF, then you basically get a decrease in density. So the plasma features are matching very well with what we find from the magnetic field, which is what you'd expect. And again here, this is a cut which is in a plane which is perpendicular to the current sheet or the neutral sheet, and it's very, very thin at the back here. And this is basically the plane where we have all our separators lying. They lie in sort of almost a flat plane. The bow shock here, and you can get the cusps if you look at a vertical cut. Velocity, again here, this is a very strange sort of velocity flow. You'd wonder why on earth do you get this pattern, but once you know what separatoric surfaces are like, then you can explain why does it look like that, why is it all snaking up to here. Well, this is basically where you've got reconnection and you've got a strong outflow jet. So that's why it's coming from that point. Again, here, there is reconnection from this point, and this point, giving you strong outflow jets in that direction. Around here, strong outflow jet back here, and again here, strong outflow jet. And again here, you can see that you can't see the blue. The blue, unfortunately, blue on blue doesn't work. But there's a blue separatoric surface which is containing this basically fast outflowing plasma behind. And again here, these wiggly lines are all associated with the separated surfaces. So when you know them, you can say something about what the plasma flow and behaviour like, because of course the plasma is contained within these regions. We can also look at the E-parallel, something I keep going back to because it's important for reconnection, and all the regions of high E-parallel, these yellow regions, have all got little orange crosses, which are all the separators around them or in those regions. It's not a perfect one-to-one because this is not looking at the integral of E-parallel. I've said isosurfaces of integral of E-parallel, that's not true. This is isosurfaces of E-parallel. It does say E-parallel. So what I've just said is wrong. These are isosurfaces of E-parallel in this plane, not the integral of E-parallel. And again here, you can't really see the strong regions of E-parallel. There's white around here, but there is yellow within this region, but it's so confined to where the separators are that you basically can't see it in this plane. And we can look at the time evolution of this, just pausing it here at some random time. Again, you can see these regions are all associated where the separators are. And down here again, you can just about see there's kind of a bit of a blue region through here where we've overplotted blue and red lines, which are separated surfaces. So from all of this, what can you tell? Well, all the regions of high E-parallel are threaded by separators. You can look at the particular types of separators, or the cluster separators, they're not very interesting. But the day side separators, the night side separators, are going to be their typical, how many there are, their typical lengths. Obviously the night side ones are much longer. The integral of E-parallel along them, how much is there? And then the location relative to the Sun-Earth line. These go back very far, much further than anybody might have imagined, and they've never actually sent probes this far out because they never thought anything useful would be happening that far out. Or say useful, interesting happening. We can look at connectivity maps as before. Cyan is the interplanetary magnetic field. Yellow is the flux that's connecting to the Sun. Green is from the Earth to the IMF, and blue is IMF to the Earth. And the separators are drawn in green. They really should have been drawn in different colours. But you can look at the time evolution of these things, and you can see from the time evolution that basically, it goes very quickly, that you are having flux that's changing many times. You've got this multiply reconnected flux again. Now what I'm going to plot here is basically the evolution of the flux from the Earth. So imagine this is longitude down here, this is latitude. This goes from 0 to 360, and then I've plotted basically this extra 90 degrees on this bit here over there, and this bit here over there. So because this is basically where most of the interesting stuff happens. This is 0 degrees is effectively the Sun-Earth line. So this is the point, kind of parent line next to the Sun. Nearest point of the Earth towards the Sun. And if you look at this, you can see that there's a change the whole time. Now, if we simply plot how much flux is connected from the Earth to the Earth, well, there's a bit of a change to begin with, but that's when the whole model is setting up. But towards the end, it's almost a flat line. And again here, how much flux is connected from the Earth to the IMF, or vice versa, IMF Earth, exactly the same. Then that's basically almost a perfect straight line. Now this suggests that there is no reconnection going on, but there is in fact reconnection going on. It's just when you look at in particular locations, as you convert some flux, there's another location which is doing the opposite. Okay, so if you just look at the total amount, you don't see it. So you've got to actually look at how much is changing, and that's plotted here. It's decreasing because obviously we get a big lot as it sets up, and then it's kind of leveling off at quite a low value here, but it's still happening. It's not absolutely stationary as some people think it should be. Now, the way we've calculated the sort of reconnection, or the change of flux in time here, is through looking at the surface of the Sun, surface of the Earth. Well, I keep saying Sun. And at one particular time, this comes out to be about 2 times 10 to the minus 3. But if you look at the rate of reconnection from the separators, then you find much higher estimates. And this is because this approach of looking at the flux is not very good. It doesn't actually measure all the flux that's being reconnected. You need to look at the integral of E parallel. These are giving you much higher estimates. But further work needs to be done to properly understand and explain this. So to finish, 3D magnetic fields are highly dynamic. There are many null clusters with many, many null points in them, and there are many, many separators. So the null points and null clusters, well, are created and destroyed in pairs. The nulls are usually found in clusters. The clusters may have 0 and non-zero topological degree, and the clusters may have a dominant null to which all intercluster separators go. So this will be a null point that lasts for a long time and is the dominant one, even though there are many other little nulls around it appearing and disappearing. And you can have dominant nulls in clusters that have 0 or non-zero topological degree. Separators, well, there are 2 key types. There are cluster separators. These are the little short ones that just connect nulls within the same cluster. They're usually sort of one separator per null pair. They're short and small, integrated parallel. The key ones are these intercluster separators that connect nulls from different null clusters. They are separators that connect nulls from different clusters, say that properly. There's commonly many of them, lots of them going on, which means that you will get multiple separator reconnection, which is probably connected with turbulent reconnection. So here, these are the ones that are globally important for restructuring the magnetic field. And finally, separator reconnection. Not all separators show reconnection, depends on basically the plasma around them. The reconnection occurs locally somewhere along the length of the separator, not at the null points, associated with a counter-rotating flow. And your field may be of X-type or O-type in the planes perpendicular to the separator. And here, why are these things important? And what are their consequences? Well, they can provide fast reconnection in that you can process a lot of flux, basically at multiple different locations, not just at one location. This used to be a big question in reconnection. Can you get fast reconnection? The answer is yes, it's dead easy in 3D. You just have lots and lots of locations to do it in. You can have multiple widespread energy release. This is important because, as I said beforehand, if you put energy in one particular location, it will spread along the field line but not across it. So how do you heat a large area? Well, the only way you can heat a large area is if you have many energy release sites. And this is basically what we're finding from our 3D work. And also, because of this multiply reconnected flux, so your flux is reconnected many times, you can get long duration events. You get a long energy release. It's not something I've shown in this talk, but you can show it from the work that I've done. So, thank you.
Can you say, just very briefly, what is the model you've used? Is it the full MHD equations in a compressible fluid and fully three-dimensional computation?
Yes. So all these numerical works have actually been done on about 3 different codes, but all of the codes are fully 3D, resistive, incompressible. You have
incompressible is
definitely incompressible.
Okay. Yeah.
Sorry. No. Wrong way. Compressible. They're full.
There's
full.
a difference.
There's a huge difference. There's a huge difference. So the full MHD equations, basically.
And so thermodynamics you bring in as well?
Okay, so what we don't get right in the thermodynamics is we don't have properly thermal conduction along the field lines. So our heat distribution is not right, and nor do we have radiation. But we are doing models now that do have these things in. In terms of the evolution of the magnetic field and all the things that we're seeing, it doesn't make any difference. But obviously in terms of the energy deposition, it makes a big difference.
It's interesting to know what all these beautiful pictures are actually based on. And so it's an amazing achievement, I think, to carry out computations of this complexity and extract so much information from it.
So the carrying out the computations is relatively easy, in that once the code is set up, then you can put things in and you can run them.
What sort of code? I mean, what?
So we run them on parallel machines, and we've used the Copenhagen stagger code, which, although it says Copenhagen stagger code, it's actually written in St Andrews. And Layer 3D, again, written by a member of staff who used to work in St Andrews. And then the magnetosphere one was done using Jimmy Rader's code, which is actually anybody can use. You can just ask for it to be run online. But this was actually run special commission for John Dorelli. So actually running it is fairly easy. What's difficult is doing the analysis, and that has taken us many years to get tools that can show us what we want to see. Or
Post-processing.
yes.
You got a picture of tubes reconnecting to sheets. Do you have any pictures of tubes reconnecting to tubes?
Right. So that you're thinking very, very, very back at the very beginning. Yes. I mean, okay. The situation you see here, the magnetic field is everywhere. So I can choose any isosurface of flux that I like, and I can then plot it. So I can make something look like a tube, or I can make it look like a sheet, depending on what I choose to colour and plot. The point is, magnetic field is everywhere. So for me, what is a flux tube? Where is the boundary of the flux tube? Where does it stop? Where does it start? So that's what on the sun, I don't normally think in terms of flux tubes or things like that, because they're not particularly well defined. But yeah, I mean, the beauty of these things is actually you can draw what you like. Well, in many ways, you can kind of highlight and pick out things that you like. The key thing is to pick out the most important things that are occurring, and to try and sort of understand exactly what's going on. You can be led astray by many different kind of plots and things that one can draw.
I know what you want to know whether the helicity is conserved.
Okay, so I can say something about your helicity. So in all the experiments that we've looked at, the helicity is effectively conserved, or pretty much conserved. What you find is, for instance, that your writhe is converted to twist or vice versa. And so you just get a transfer of the helicity from sort of one place to the other. So so locally, it can be effectively kind of changed or destroyed in some ways. But globally, it must be all conserved. So within your domain, it's conserved, but locally, you can get a change of helicity and a rate of change of helicity. In fact, that's related to, I talked about the integral of E parallel. I didn't say whether that integral of E parallel was counting positive E parallel or negative E parallel. Now, depending on the local helicity in a region, will tell you whether your reconnection is associated with positive E parallel or with negative E parallel. Because the reconnection, all it can do is reduce the helicity. It can't increase the helicity. So it must be of the appropriate sign that you locally reduce the helicity, although globally it's all conserved.
Rob.
So I don't know enough about hyperbolic equations, but when you drew pictures of shocks, and then later you said in response to Keith's question that radiative effects, so speed of light effects, you don't take into account. So this is a question for everybody, because I just know, but in the presence of shocks or even radiative effects that aren't modeled here, do you preserve, again, things like helicity, or is that out the window or out the, does it fly off too? I just wonder if someone could clue me in, because it's a new feature I have never thought about.
The shock here is a plasma shock.
Right.
So
it's a sun,
so what the shock is doing to the magnetic field is making the field lines bend in some particular way. I don't know that it's necessarily introducing a particular twist or a writhe or something like that, so I'm not sure that that's actually changing your helicity. Because all you're doing is as your field goes through your shock, is it kind of bending one way or kind of bending another way. That's basically what it does.
Well, the complexity of these magnetic field 3D diagrams you showed us is quite reminiscent of what we saw during the month of September, the complexity of the structure of protein molecules. Very similar, extremely elaborate structures with similar reconnections going on. So it gives some justification for our attempts in this program to to unite these two fields. Anyway, it's given us a lot to think about. We're moving into magnetohydrodynamics. Of course, we have a workshop, satellite workshop coming up devoted to this topic in Edinburgh in a couple of weeks' time. So thank you, Claire, for introducing us to this field.